Alright guys, so we're going to be working with Taylor polynomials for a few weeks actually, so there's a lot to do with these things. Today we're just learning what they are, what they're used for, and just kind of the basics. So make sure you've got a calculator, and yeah, we'll go from there. So we have been asked a lot, and this is what we do in AB, to approximate a function value using a tangent line approximation. So if I want to approximate the sine of 9 pi over 48 using a tangent line approximation for the function sine of x at this point of tangency, x equals pi over 6, then remember for that we need a point and a slope. So the point would be f of pi over 6. This is the point of tangency. So sine of pi over 6 is 1/2. So we've got the point pi over 6, 1/2. We need a slope for our tangent line, which would be first figuring out what is f prime of x. So the derivative of sine is cosine. Evaluate f prime at pi over 6. So cosine of pi over 6 is radical 3 over 2. So this gives me my tangent line, which I'm going to use to approximate a value. So the tangent line in point slope form would be y minus 1/2 equals radical 3 over 2 times x minus pi over 6. And so if we wanted to approximate the sine of 9 pi over 48, we could plug that into this equation. Radical 3 over 2 times, let's make this 9 pi over 48, and then instead of minus pi over 6, we'll just get that common denominator, 8 pi over 48. And then this 1/2 needs to get added to the end of that. So whatever this comes out to, radical 3 over 2 times, that'd be pi over 48 plus 1/2. This would be our approximation for the sine of 9 pi over 48. And if we want to see how far off that is, because so we're only 1 pi over 48 off from that point of tangency, we can pop this into our calculator. Let's see, I've got to switch to radian mode. So we want to evaluate and see what this comes out to. So this was square root of 3 over 2 times pi over 48 plus 1/2. So I'm going to write this down to all of its decimal places because we're kind of looking to see how far off are we. So our approximation for the sine of 9 pi over 48 is 0.556681230 and then let's see what the calculator says the actual value of the sine of 9 pi over 48 is. So this is still an approximation because it's rounded, but let's just go ahead and say sine of 9 pi over 48 is equal to, according to our calculator, 0.55. So we match to 2 places, but then it strays from there. 5, 5, 7, 0, 2, 3, 3. So the tangent line approximation, in this case, it's pretty good. It's 2 decimal places accurate, but we want to see if we can do better. So we kind of talked about accuracy with alternating series, and our amount of error or our remainder is going to come into play with these Taylor polynomials too. So if you think about what we're doing with this, we're using a line to approximate a function that we know has a curve to it. So, you know, the line and the curve are equal at that point of tangency, but then as soon as you stray from that point, they no longer match up. And then the further you stray away from the point of tangency, the further off the actual approximation from the actual value becomes. So it would make more sense if we're thinking about coming up with an estimate of a function value to use a curve instead of a line. So we want to approximate a function value with a curve. And so this is the BC way. So if you've had AB before, Calc 1, you're not using curves, but we're going to generate some sort of a curve to figure out, like, well, maybe the curve matches up with the curved function a little bit better than a line would. So it might still be an approximation, but it'll be a bit closer. Functions that are easy to work with as far as taking derivatives and integrals are polynomials. Think about those power rules. And polynomial graphs are curved and smooth, so it seems natural that we would use some sort of polynomial function. So a couple of things I want to talk about before we get into developing this. We want to look at, let's make things easier. Like this point of tangency that we used was pi over 6. Instead of that, let's just think about some curve. I don't know, this is my curve, this is my f of x. And then let's say that we want our point of tangency to be x equals 0, because that's going to make building our polynomial a lot easier to see patterns for. So maybe we're going to use some sort of a curve like this to try to approximate that f of x. So I'm going to call this p for polynomial. So in general, a polynomial function, let's just call it p of x. Let's say p of x, I'm going to go backwards. It always has, or it could have some sort of constant. We'll call that a sub 0. And then it could have a linear term, so we'll call that some coefficient a sub 1 times x. And it could have a quadratic term with a coefficient a sub 2. And there's no limit to how many terms or what degree our polynomial could be. So let's just say plus dot dot dot. There'd be some nth term. And this could go on forever. So you might see kind of how this is going to connect with our idea of infinite series. We're adding up a bunch of terms. And in some cases, we'll be doing that infinitely. So how do we know what polynomial to pick? Like for this f that I drew, maybe I pick something quadratic, but maybe something to the 4th power would be more accurate. And even if I figure out what degree I want, how do I make sure, like how do I figure out these coefficients in front to make the thing kind of hug close to f of x? So again, I'm just going to make a note here. To figure out this pattern for simplicity's sake, we're going to say our point of tangency is x equals 0. And we're going to point out some things that should be true at x equals 0. So if that is the point of tangency, then it has to be true that the actual function value f of 0, that has to equal p of 0, right? Whatever the polynomial is at 0 has to match f at 0, because that's the one point that they share, that they have in common. And p of 0, go back to this polynomial function. If we plug in 0 for all of these x's, all of these terms are going to drop off, and we'll be left with whatever that constant a sub 0 term is. So I'm going to try to develop a pattern. So off to the right, let's go ahead and say, all right, we're trying to come up with a formula for, like, what are we going to put in for a of 0? So now we know a of 0 should be whatever f of 0 is. Okay, so we want that function value to match. Now, the second thing we want to be true is we want the behavior of f to match the behavior of p, meaning, like, if f is decreasing at that point, I want p to be decreasing. If f's derivative is 0, I want p's derivative to be 0, etc. So if we want their derivatives to match, like we don't want f to have a negative derivative and p somehow has a positive, because that would mean that one function is decreasing, one is increasing. So if that's the case, then we want to make sure that f prime of x, the derivative of f of x, is equal to p prime of x. We want that to be true at 0 for sure, but first let's figure out what that formula is. So again, I'm referring back up to this p of x when I'm looking at this. What do I get when I start taking the derivatives of these terms? So when I take the derivative of the constant term, it's gone. When I take the derivative of a1 times x, I'm left with just a sub 1. Let's take this out to, I think I'm going to take it out to a 4th degree term, just so I have enough terms to work with after this. So let's start writing some of these out. Take the derivative of this quadratic term here. You would get, remember power rule, you'd get 2 times whatever a2 is, times x to the first power, plus, pull out the 3 a sub 3 x squared. And I didn't write these terms, but hopefully you're seeing a pattern. Let's take this out to coefficient of 5. So 4 a sub 4 x to the third plus 5 a sub 5 x to the fourth, and then we'll just write plus dot dot dot. The reason I'm writing this many terms is because we're going to be taking successive derivatives. I want to have enough to show a pattern here. So we want f prime of x to equal p prime of x at the point of tangency. So again, let's figure out what's happening at the one point that they share. We want these things to be exactly equal. We want f prime of 0 to equal p prime of 0. All right, so if I plug 0, just like before, if I plug 0 in for all of the x's, all of these terms are going to drop off, but I'll be left with a1. So again, a1, switch colors for this, a1 is equal to f prime of 0. So remember what we're trying to do. We're trying to figure out a formula for, like, what is this p of x supposed to be equal to so that it hugs f of x nicely. So far, we have some more information. We have that the constant will be whatever f of 0 is, because we'll have some f of x that we can plug into at the point of tangency. We know that value. And now we know that this a1 is f prime of 0 times x. Okay, so what about a2? Well, a2, if you think about this, we also want the concavity of p to match the concavity of f. It wouldn't make any sense for f to be concave up while p is concave down, because then every point past that point of tangency is going to be really far off of what it should be. So let's make sure that their second derivatives match. So the second derivative of f should equal the second derivative of p at 0, but first we have to figure out what the second derivative of p is. All right, so take a derivative of a, that constant, and that goes away. And then you're going to get 2a2 times 1. And then power rule again, you're going to get plus 6 times a sub 3 times x, plus 12 times a sub 4 x squared, plus 20 times a sub 5 x cubed, plus dot dot dot. This could go on forever. We want to make sure that this is true, that the concavity matches at the point of tangency, which is at 0. And again, I picked 0 because you can see it's really easy to plug 0 into stuff. So everything falls away except the constant term. Now this is the first one that I'm trying to build. I'm trying to solve for the a's in each of these. This is the first one I've got to do a little bit of math. If f double prime equals 2 times a2, then a sub 2 is equal to the second derivative of f at 0 divided by 2. All right, now we've talked about function behavior, concavity. Once we get to third derivatives, I'm sure there's some sort of application for this, but we're really just matching up the same thing. The more terms, the more derivatives that match up between f and p, the closer p will actually be to matching f beyond perhaps that point of tangency. So I don't have a good context for what does it mean to match their third derivatives together. But we're kind of just going through the same pattern. We're going to take this to, I think, just 4 derivatives, and then we'll go from there. So look back to your second derivative line and start taking derivatives of that. The constant term goes away. You've got 6 a sub 3 times 1 plus 24 a sub 4 times x plus 60 a sub 5 times x squared, etc. We want the third derivatives to match at the point of tangency, which is 0. We'd be left with 6 times a sub 3. So now we have a formula for a sub 3. It is the third derivative at 0 divided by 6. I'm going to do one more round of derivatives and then see if you can start coming up with a pattern for maybe not involving this 0 term. You could if you wanted to, but relating the n for which term we're at to this formula over here. How do they match up? All right, so one more round. Fourth derivative, notation for that is we're done with tick marks. We just write a little 4 up there. Fourth derivative of x matches fourth derivative of p. Constant term goes away, and now we've got 24 a sub 4 times 1 plus 120 a sub 5 times x, etc. Evaluate at 0 because that's the point of tangency where the two functions are equal to each other. And you're just left with 24 a sub 4. So a sub 4 is equal to, oops, I wrote p sub, I meant f, the fourth derivative of f at 0 over 24. All right, so think about these numbers. I am going to, because I can copy and paste, I'm going to try to copy and paste them. Save a bit of time here on the video. It'd be a good idea to have these on the next page. Okay, so do we see a pattern? That's a good question. Now, pasting is always, of course, pasting never works that well for this document. Let's see. Here we go. So I'm going to bring these up here. Okay. Do we see a pattern? Can we come up with a sub n? What is the nth coefficient going to be on the nth term? I think it's easy to match up the derivatives, right? The derivative number matches the term that you're on. So this would be the nth derivative of f. All of these are being evaluated at 0 for the particular one that we're looking at. And then maybe if I would have taken this out one more term, or if I look at what the next one would have been, I always feel like that's the giveaway. If you're not sure about these numbers, technically we've got over 1, over 1, over 2, over 6, over 24, over 120. If you don't recognize those as the factorials, again, make sure that you have that list. This is 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, etc. 4 factorial is 24. To me, it's the 120 that's always the thing that sets off the bell in my head if I didn't pick it up. But this is over n factorial. So that is our pattern. We could generate for any of the coefficients now. We have a pattern for how to set that up if our point of tangency is 0. So what we're saying is we've got this polynomial now. And we could set this up as a series, but before we do that, I'm going to write out the terms. So instead of saying a sub 0, I can say the constant term was f of 0, right? F of 0. Now, technically, that's over 0 factorial, but remember, 0 factorial is 1. And then we have the first derivative at 0 times x over 1 factorial. And then the x squared term is the second derivative of 0 over 2 factorial times x squared. I'm going to put plus dot dot dot. The nth term would be the nth the nth derivative at 0 times x to the n over n factorial, and this could go on forever. So a lot of times for these problems, you'll be asked to write the first 3 or 4 non-zero terms and the nth term like that, and then you would just show that it continues on forever. We can write this like a series, right? This is an infinite series. The first n starts at 0. It could carry out to infinity. And the formula for it is just our a sub n times x to the n. So a sub n is the nth derivative at 0 times x to the n over n factorial. A sub n just gives you the number in front of the x, x is going to be to the n power because that matches the term number. Okay, now this is a special case. This series right here where we looked at a center, a point of tangency at 0, this is called a Maclaurin series. A Maclaurin series, or a Maclaurin polynomial. I'm kind of merging a couple of sections together, sorry. A Maclaurin polynomial, which could be written as a series, so interchangeable. It is a Taylor polynomial, or a Taylor series, with a point of tangency at 0. So it's a Taylor series, or a Taylor, I'm going to write that, series slash polynomial. Same idea. With points of tangency at x equals 0. It's got a special name. The AP test will use the phrase write the Maclaurin series for whatever. So you'll see some practice on that. What if we're not centered at 0? So let me scroll back up for a minute. I centered at 0 so that it would be easy to plug in 0 and let everything kind of fall away. What if it's like our previous example where we're centered at like pi over 6 or something? It does not change much to the formula. It's just that instead of having x and x squared and x to the third, you've got to incorporate, if the center is off of 0, you've got to incorporate that by saying you're going to have x minus c, where c is the center, to the n power. So like think back to the tangent line that we had. Back to that tangent line equation. I had x minus pi over 6 as part of that tangent line equation. And that's because that's our point slope form, but it's also like a little mini polynomial, right? A linear function is a polynomial that helps you approximate a function. So anyway, if you plug in your point of tangency, which would be c, you would get back to 0. You're still going to have the nth derivative, but you're not always going to evaluate at 0. You'll evaluate at whatever the center is. And you're still going to have n factorial in the denominator. This is what a sub n would equal. Oh, I'm sorry. This is what the series would equal. From 0 to infinity. So the series, the Taylor polynomial series would be this. If you wanted to expand it out, it just means, okay, our p of x, our Taylor polynomial, would still start out with not f of 0, but f of c, where x equals c is the point of tangency. F of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial. I didn't write the over 0 factorial over 1 factorial. That's optional. I'm going to write one more term times the third derivative plus the third derivative at c times x minus c to the third over 3 factorial. You could carry this on forever, right? Okay, so what we've just done is generate a formula that will allow us to come up with what's now we're going to call a Taylor polynomial that will be used instead of a tangent line approximation. These are basically tangent curve approximations. So write the Maclaurin polynomial for f of x equals e to the x. Oh, one more vocab thing. When I say that the point of tangency is, in this case, Maclaurin, x equals 0. Another way to say that, instead of always saying point of tangency, we use the phrase centered. The polynomial is centered at x equals 0. So that point of tangency is sort of the center, and then we imagine that the polynomial from there goes in both directions and strays from the function in some degree. All right, so let's remind ourselves what we're doing here. We have f of x equals e to the x, and we're trying to come up with some sort of Taylor polynomial, which we have, or some sort of Maclaurin polynomial, which we have a formula for. It's going to be f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus dot dot dot. So we need to come up with what these values are going to be. Let's take this to 4 derivatives just so that we have enough information. So I always start like this. I like to write out what f of x is, so I have something to work with. First thing I'm supposed to do is plug in the center, which is 0. E to the 0 is 1. Next thing I'm supposed to do for the next term is find f prime of 0. So first find f prime of x. Derivative of e to the x is e to the x. Evaluate at 0. So maybe you've already figured this out, but it doesn't matter how many derivatives I'm going to do. I'm going to keep getting e to the x. There's no, if this were like e to the 2x or something, there'd be a bit of chain rule happening. But all of these coefficients are going to just keep being 1, e to the 0. Okay, so maybe I don't need to take 4 derivatives. What I have now is that e to the x can be written as, I'm going to say equal to for now. We'll talk about like how accurate is this Taylor polynomial? Is it just accurate at the point of tangency, or does it do better than that? We'll talk about that in the next like week or so, but for now we can go ahead and write equals. They do match up for quite a while for e to the x. So now I know e to the x instead of f of 0 is 1 plus 1 times x plus 1 times x squared over 2 factorial. I know I can simplify 2 factorial, but it's best not to because you might pick up patterns a bit easier. Let's take it out to 4 terms. X cubed over 3 factorial plus, there would have been a 1, x to the 4th, 4 factorial. Let's put plus dot 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 plus. So what is the nth term here? We can come up with a formula pretty easily, right? Every term just has a 1 in front of it, so I'm not going to write anything for that. It's all just x to the n over n factorial. So we are sort of going to be coming up with patterns here. And this is knowing that n starts at 0. That would be x to the 0 over 0 factorial. That does give you 1. Whatever you write for your general term here, this is called the general term, it has to be true and work for every single term that you're showing in the series. So just be aware of that. This is something to memorize. We will have certain functions like e to the x that we use Taylor or Maclaurin polynomials for a lot, and so one reason to memorize is just for efficiency's sake, so you don't have to keep doing this. But another reason to memorize is because we'll be kind of combining functions toward the end of this chapter, and it will be nice just to build upon this rather than generate something new every time. All right, let's do another example. So got some new vocab for you. Find the Taylor polynomial P4 for f of x equals ln x centered at c equals 1. So remember, that's our x equals 1 is our point of tangency. That's what that means. It means that we will be plugging in and evaluating derivatives at 1. What's this P4 talking about? So that number down there is called the 4th order. Order refers to the number of derivatives that you need to take, which usually, but not always, refers to the number of terms. Usually, but not always, refers to the number, refers to the degree, but it doesn't have to be. So the order is strictly the number of derivatives. Depending on if some of the terms become 0, you may or may not have terms that match or degrees that match. So all this means is you've got to take 4 derivatives. All right, so write out the function. Evaluate it at the center, because the first term, the constant term, is what f of 1 equals. Natural log of 1 is equal to 0. So far we have this. Natural log of x is equal to 0 plus derivative of natural log is 1 over x. Evaluate the derivative at 1. 1 over 1 is 1. Now we have 1, I'm not going to write in the 1, but 1 times, remember it's not x, it's x minus 1 over 1 factorial. Okay. And then, here, let me do this. The next term is going to be something times x minus 1 squared over 2 factorial. Right? So let's figure out what that something is. What's the derivative of 1 over x? Remember, this is x to the negative 1. So that becomes negative 1 over x squared. Evaluate that at 1, and you get negative 1. So I wrote plus here. I guess I should have written minus. Take the third derivative. Remember, this is negative x to the negative 2. So that's going to become positive 2 over x to the third. Evaluate that at 1. Now I'm getting something different. 2 over 1 is 2. So plus 2 times x minus 1 cubed over 3 factorial. Fourth order means I have one more round of derivatives to take. Fourth derivative of x. This is 2x to the negative 3, so this becomes negative 6 over x to the fourth. Evaluate that at 1. Get negative 6. So my last term is negative 6 times x minus 1 to the fourth over 4 factorial. I made a mistake back here. I wrote ln x equals, but there's no way that if you're not using an infinite series, if you're not allowing it to go on forever like I did for the e to the x, this can only ever be an approximation. Just like with the alternating series test that we had, we said we can approximate it by using maybe a sixth partial sum, and then the error is the seventh term. So same idea here. This is just an approximation for ln x. And the way that we can use these functions, by the way, is like, now if I want to predict ln of 3, I can plug 3 into the polynomial side and do some math and get what that approximation would be, which doesn't seem like that great of a thing, but it will help us when we want to take derivatives and integrals and things like that. All right, so last page here. Find the fifth order Maclaurin series. So again, fifth order means P5, which means we need to get to 5 derivatives. Doesn't have to be the number of terms, does not have to be the power. We'll just see if that's where we get. F of x is sine x. It's Maclaurin, so centered back at 0. Write down f of x. Evaluate f at the center, which is 0, point of tangency. Sine of 0 is 0. So right now we have this. Sine of x is approximately equal to 0. F prime of x, derivative of sine is cosine. Cosine of 0 is 1. So now we have plus. It's normally x minus c. It's just going to be x because x minus 0 is x. You don't have to write over 1 factorial, but you can. Second derivative. Derivative of cosine is negative sine. Evaluated at 0. Still 0. So technically we've got plus 0 x squared over 2 factorial, but yeah, that's going to go away. Third derivative, we've got to get to 5 derivatives, remember. We get negative cosine x. Evaluate that at 0. Cosine of 0 is 1, so this is now negative 1. Now I've got minus x to the third over 3 factorial. Fourth derivative. Derivative of negative cosine is positive sine. Evaluate that at 0. You get 0. So it'd be plus 0x to the fourth over 4 factorial. One more derivative. Back to cosine. Evaluated at 0. You get 1. So plus x to the fifth over 5 factorial. Let's clean this up a bit because the zeros, simplifying is not required, but you're going to want to have these patterns. So sine, if you notice, all of the negative exponents are represented. We only had to go to the fifth order. But if we were to carry this on forever, the next term would be minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. So it is alternating, and it is just odd exponents. This is another one we're going to memorize eventually, but we'll memorize a more generic form. Note about this. This was fifth order, right? If the problem would have asked for sixth order, you can do that, but the sixth order looks like the fifth order because the sixth order, the sixth derivative is back to negative sign, and that's 0. So for some of these Taylor polynomials, when some of the derivatives are 0, the order will not have to match the degree, and it will not have to match the number of terms. Like this last example was fifth order. It was fifth degree, but it didn't have 5 terms. It only has 3 terms, if you're talking about non-zero terms, which we usually are. So you just have to read carefully on the AP test. Sometimes they'll ask for a certain degree. Sometimes they'll ask for a certain number of non-zero terms plus general term, or sometimes they'll give you an order. So you just have to watch it. All right, last example, my battery might die. We'll see what happens. So this is supposed to be f of x equals cosine of x centered at pi over 3. And we want the fourth derivative. So let's just start coming up with our terms. F of x is cosine x. F of pi over 3. Cosine of pi over 3 is 1/2. Derivative of cosine is negative sine. Again, in order to beat my battery life, I'm just going to plug in, right? So negative sine of pi over 3 is negative radical 3 over 2. I've got to take this to 4 derivatives, so let's just keep going. Derivative of negative sine is negative cosine. At pi over 3, that's negative 1/2. Derivative of negative cosine is positive sine. Back to radical 3 over 2. Finally, back to cosine, back to 1/2. So cosine x is approximately equal to this fourth order polynomial. The constant term is 1/2. The linear term is minus radical 3 over 2. This is weird. Minus radical 3 over 2 times x minus pi over 3, that's the center, to the first power. I'm going to write this over 1 factorial just to show you the pattern. Next one's minus 1/2. I'm not going to write the 1, but I will write 1 x minus pi over 3 squared, and then it'd be 2 factorial still. So 1/2 x to the n over n factorial. And then plus radical 3 over 2. X minus pi over 3 to the third over 3 factorial. And out of room, so last one's going down here. Plus x minus pi over 3 to the fourth over 2 times 4 factorial, because the last one was 1/2. Use your answer in A to approximate cosine of 1. So cosine of 1 is about equal to 1/2 minus radical 3 over 2 times 1 minus pi over 3 minus 1 minus pi over 3 squared over. Now I would start simplifying this so I have less to type in. I'm not going to type it in because that'll probably kill my battery. But yeah, you're just typing all this in. Cubed over 2 times 6 is 12. Minus 1 minus pi over 3 to the fourth over 4 factorial is 24. 2 times that. So approximating in my calculator, I didn't write it down on my paper either. So we could type all that in and get something. And then now what happens if we just use our calculator to actually, type in this answer. Okay, so you get some sort of decimal approximation. What if we do type in cosine of 1? So let me see what that comes out to. in radian mode. Cosine of 1 is 0.5403023059. And you know what? I'm gonna cheat a little bit so I can see what these answers were without my battery running out. So okay. So assuming we did all of this on our own with our calculators, here we go. So we did that. We typed it in, got this. How closely do they match up? How many decimal places are they the same? Oh, wow. Look at that. 1, 2, 3, 4, 5, 6, 7, 8 decimal places of accuracy. That's pretty cool because our line, when we did a trig function, our tangent line was only good for 2 decimal places, and this is 8 places. That's pretty cool. And what does that look like in terms of error? What's the error between our approximation and the actual value? 8 places should coincide with your scientific notation. This means put 8 zeros in front of that -17, right? So put 8 zeros in front of that, and yeah, those zeros should tell you how many places you're going to match up exactly before you finally stray. See how there's a difference of 17 between 42 and 59. So pretty good, not bad. We only had 1, 2, 3, 4. So a 5-term polynomial, a degree 4 polynomial, can predict or approximate a cosine value that accurately. It's actually pretty impressive. All right, we're stopping there for today. Your homework is homework number 21. Enjoy.